Okay, hello class. For this presentation, I will talk about centroids because I believe they are significantly important for engineering, since it's good to know how to build structures that will adapt to the centroid of your body, such as this water tower, for example. We need to build the beams or the structure strong enough in order for them to be able to support the centroid of this water tower here, because if not, then the beam could collapse, the structure will collapse, it will be a disaster, basically, and a lot of money loss. Now, to explain this, the center of mass, center of gravity, and the center of the area will be at the same location. This location is known as a centroid, as the name says it, and will be located in the center of the body, or the geometric center, assuming the body is homogeneous. From chemistry, homogeneous meant that it had the same density and was made out of the same material all throughout. For this example, I will choose to talk about mass as a centroid for the example. It doesn't matter because they all have the same location right here. So if I were to balance this entire structure on my finger, it would balance perfectly on my finger at this point here. This is because that's the centroid, and that's where all the mass is going to concentrate upon here, as if the weight of the object is acting along that point. So it says if all of the weight's going to act on this point right here. Now, how do we find the centroid? Well, for this specific point, or this specific body, it is in the x and y coordinate system here. For this rectangle, it will be half the distance of x and half the distance of y, because that's going to give you the center right here. Same thing could go for a circle, or for a triangle, or for any shape that's not too complicated. Now, what if the body wasn't homogeneous, meaning it had a different density, or it had different densities, and it wasn't all the same one? Take here, for example, iron, and take here copper as an example. The centroid will no longer be at the center. It would most likely be somewhere around here, because iron has greater density than copper. I hope. For this video, I will focus on the centroid for an irregular shaped body. Now, what is an irregular shaped body? An irregular shaped body is a body whose centroid cannot be easily found because we don't really know the shape of it or the geometry. Say, for example, a cylinder. We actually know the shape of a cylinder, and we know its area, we know its symmetry, and everything. And we also know that centroid lies along its axis, along the z-axis, and halfway along the x and halfway along the y for this. But what happens when we have a shape like this we're dealing with? We don't really know a lot about this shape. But what we do know is that the same concepts apply. The centroid is going to be located in the geometrical center of the object. Also, it's going to be as if the entire weight acted upon the center point right here, assuming the body is homogeneous, same density all throughout. Now, just like before, the centroids are going to have their own coordinates. It's x and a y coordinate. Well, for this one, we're in 2D, so it's going to have an x and y. If you were in 3D, it would have an x, y, and z. Now, the coordinates start from the center, or from the origin. From the origin all the way to the x coordinate, and from the origin all the way to the y coordinate. Now, for this shape, we cannot really use simple math we are used to. We need to use calculus, basically. Now, how do you find the centroid for this shape then? Well, you would go here. What you would do, you would get this shape and divide that into an infinite number of strips. Each of these strips has their own centroid, their own length, infinitesimal length dx and dy. That's what you would do. So analyzing this strip here, it's going to have its own centroid, and it's going to have its own x distance and its own y distance here from their centroids. And these here are x theta's and y theta's. And these are to know that you're looking at an infinitesimal small weight dw. Here. And you could say this is an infinitesimal small dx, and you could take an infinitesimal small dy. As so. Now, here we have all these strips here, and all these add up. So if you add up all these components, the x, theta's, and the infinitesimal weights together, you're going to get the x-coordinate of the centroid times the weight. And that is equal to the integral when you add all these pieces together right here. Now, we see this integral here, but we're interested in finding the x-coordinate and the y-coordinate. So what you would do, you would move the weight to the other side. You would factor, or not factor, sorry, or just isolate the centroid x. dw, and you have here's the weight. Now this weight here could be defined or said as the integral of all the infinitesimal dw's, infinitesimal weights. So this could be written as dw. Same goes for the y. I chose this image from the book because I think it explains centroids pretty well in 3 dimensions. Here you see the centroid due to the center of gravity. Now, this centroid is going to have its own x-coordinate, y-coordinate, and z-coordinate to its centroid. Now, an infinitesimally small weight dw is going to have its own x theta, y theta, and z theta. As we know, this pandemic isn't over yet, so we need to give this blob a mask. Right here. Now imagine if all these squares were infinitesimally small dw's. Each of these squares, or dw's, or infinitesimally small weights with their own x theta, y theta, and z theta components or coordinates. Here. Now, summing all the dw's up, you're going to get the entire weight of this body. Another way to look at centroids, or to find centroids, is by looking at the moments. To explain this, imagine this dw here, this infinitesimally small weight, is the same as this one here. Now, I'm going to zoom in to the coordinates I drew. Alright, so imagine a force exerted by the infinitesimally small dw. That goes along the y here. And it will cause a moment along the x, about the x here. Moment about the x. Okay, now take this equation here. What you're doing is that you're summing all the y thetas to the infinitesimal dy's, because this is occurring along the entire body. Giving you the magnitude of the weight times the entire distance y to the centroid. Same goes for the x. Here. Imagine a force due to the infinitesimally small dw that runs along the x, causing a moment along the y and y. Same as before, you're summing all the x thetas to the infinitesimal dy's along the entire area, giving you the equations for the centroid, or define the centroid. It's worth noting that the center of mass acts in the same location as the center of gravity. So I'm just going to show that with this derivation right here. So you have W have dm times gravity. Oh yeah, by the way, this is equal to the weight times mass times gravity. So that's the reason for that. Okay, divide that by the integral. These g's cancel out. And then you're left with the center of mass. Right here. And now I think I should just talk about this a little bit, real quick. Now, as I said before, these locations for the center of gravity and the center of the area will be basically in the same location. Right here. The only difference is the variables change. This is an infinitesimally small dy. This is an infinitesimally small d area. I'm talking about this because I'm going to use the area to solve problems later, or to solve my example. Centroid of an area, centroid of mass, centroid of gravity. It doesn't matter, it all acts along the same geometrical center of the body. Now, I'm talking about centroid of the area because I'm going to solve an example based on the centroid of the area. Here you can see a body defined by a function. Right here. As stated before, you have your centroid, your x-coordinate, and your y-coordinate to the centroid. Now, when we evaluate the centroid, we're going to do these based on these equations here. Now, to evaluate these problems, we need to do them based on strips. Now, I'm going to explain these strips briefly or in detail, depending how I do it. Now, right here I have a vertical strip, and it says here that it is constant in the x direction, but it is cut in half in the y direction. The reason being, seeing this centroid here, we see that it's a distance half of y distance, and this vertical centroid will have an infinitesimal size dx here. Now, if you multiply all these dx's times the height y, you will get your area, as stated here. This could be a little bit hard to explain or to understand, so I'm gonna try to explain this as well as I can. Now, see this infinitesimal, or I'm sorry, this vertical strip here. It has a length dx. Now, notice how as I run this across the function, it's going to remain constant in the x direction. However, the y direction, well, in the y, it has a distance y half here from the centroid. So we use this distance to find the y coordinate of the centroid in the y direction. So we just move this here. And that's going to give us our y coordinate of the centroid. Maybe it should do that. That's good. And I also did this thing to prove it. I just did. Now, same as for for the x direction, right here. Notice how the y remains constant here, but the x this time will be divided by 2. The x to get to the centroid. I should probably change this sign here. That's better. Now, as before stated, you're going to have your x. Oops. Never mind. Okay. You're going to have your y constant as you move it up or down, and your x will still remain in the same spot, in the same location. The same location, x divided by 2. Half the distance of x. This here will give you your centroid in the x direction, or your distance here, as stated here. X centroid equals x divided by 2. And that you plug into the function. Now for the area, notice how all these strips are infinitesimal dy's. You would get those dy's and run them across the x-axis. So your area would be x times dy here. And these are the equations we use to evaluate the centroid. I should the variable here. Now we use single integration with these rectangles, and when we evaluate a problem, we do so according to the strips we choose. Finally, for this example problem, we're asked to locate the centroid x of the parabolic area. Now I'm going to write that here. Locate the centroid x here. Now recall that the equation for the centroid was going to be x is equal to centroid is equal to the integral of x2 times dA divided by the integral of dA here. And as before, we said that we need a horizontal strip because we are trying to find the centroid in the x right here. I could use this same drawing to do all my data or everything I need. Now, recall that x2 is going to be x divided by 2 here because we're at the center of the x. Dividing the x-axis in half gives us the centroid in the x direction. And obviously, estimated y is going to be a constant right here. Now, that makes our x2 equal to x over 2. Now for our area dA. Gonna make a little sketch here. Yeah, I should have used this one here. Well, too late now. Okay, now the horizontal strip has a length dy, and it's going to be multiplied throughout the x-axis right here. So that makes our area equal to x times dy. Okay, so we have everything to plug in into these equations here. I'm going to go ahead and do that right now. It equals 2 times x dy divided by the integral of x dy. Okay, now notice here how we need to do an integral. However, this is in terms of dy. So this means we need to get x in terms of y. We need to solve for x, basically. And we have this equation to do so. First, I'm going to write this. Solve for x to get in terms of y here. Now we have y is equal to a x squared. Now before I solve for x, it is important to solve for this variable a here. I'm going to explain that later on, why it's going to be important to solve for the variable a. However, okay, to solve for these, I'm going to probably erase these images here. Or I'm just going to copy it. Quick. Bear with me. Make sure I don't lose the figure or the image. Okay, cut. Now I'm going to put this here. Okay, notice how our x could be called b, and our y could be called h. So x equals b, and y equals h. I'm going to solve that. I'm going to plug these variables, or I'm going to substitute them into this equation to solve for a. So I'm going to be left with and h equals a b squared. Solving, you're going to get h b squared is equal to a. Bravo. And now plugging this a back into the equation, I'm going to have a y is equal to h over b squared times x squared right here. Now I could solve for x because I have my variable a written in terms of h and b here. So solving for that, I'm going to have y times b squared divided by h equal to x over 2. And you obviously have to square root this because I have that now. Okay, that's nice. So now we have our x right here, and we have our area. dA, is equal to x times dy. So that's going to make this out to become times b squared over h times dy. And I'm going to go ahead and rewrite this so they could be easier to solve once we take the integral. Right, now choose another color. Well, I could just solve for 1 because it is the same x after all. So, is 1/2 times b. Obviously, if you square root this function, this b squared is just going to be b, and you're going to have your h going to be 1/2, and that is your x. Same as for this here. Okay, now we actually have all we need here. We have all the components that we could plug in to find this integral. So I'm going to write here, we have all we need. Now plug into the equation to find the integral. Sorry, the centroid. Alright, I'm just gonna, probably duplicate this here just to avoid any confusion on my part. Here, okay, times dy. We'll make this. I'm sorry. That's better. dA times dy. That is going to be our area, by the way. And now I'm going to plug everything in. Here. And dA. Okay, now this is going to be equal to y over 1/2, y 1/2 times b divided by h 1/2 multiplied by y 1/2 times b times h 1/2 right here. And that's going to be divided by the area. Okay, so I'm going to solve the algebra for this part real quick. Explain this. So notice here how you have a y 1/2 and y 1/2, or a square root basically. These ones are going to eliminate their square root when you multiply them together. Same for these h's for the heights. This is a b here. So that's going to turn out to be y times b squared over h 1/2. We gotta add the dy. Gotta have the dy. Okay, dy is cancelled. Right. However, you're not gonna simplify anything for the area that is in the bottom. Right here. Oops. Centroid. Okay, so I think I talked about. So previously I was gonna say why we were going to solve for this variable here. Okay, as you can see, a could be written in terms of h and b here. Now when we take the integral, we take this with respect to h, right here, because we chose this strip over here. And this has to follow along the entire y-axis. Y-axis, which is also h here. So we're going to have to plug in h for y, making our integral being from 0 to h. So it was necessary for us to convert a, because we're going to have to use h so we could solve the algebra and find our answer, the correct answer. So bring this over here. Oops. Come on. Okay. Here's h and here's 0. These limits are the same from h to 0. Okay, now I could take these integrals. I hope. If my calc 2 wasn't, too bad. Here, y1/2 is equal to... Oh, caught another mistake. This has to be divided by 1/2. No space. Because as we said, x was going to be divided by 1/2, as stated here. And I guess you got to put them here as well. Yeah, okay, whatever. Just, it's here. Okay, now I'm going to take this integral with respect to whatever we need. Okay, now y squared b squared times h, and here I have 1, okay, 2, multiplied by 1/2. Well, because, when we take the integral, you're going to bring it down to constant. Okay, dy. Okay. And for this over here, it's going to be 3/2 b multiplied by 2, 3 h 1/2. Okay. And as we said, our limits for integration are from h to 0. Okay, I'm going to have this be equal to 1/4. here. Okay, now I'm going to plug in these values for h here. I should probably duplicate this. This is a lot of math, by the way. Okay, now I'm going to do what I said I'm going to do. Right? H and B h1/2. Okay, now these things could probably skedaddle. And this here, I think this was going to be a just equal to h. I'm going to go check that real quick. I'm doing the power of half. Nice. Okay, this is going to cancel out, and we're just going to be left with an h to the power of 1. Okay, here are our two basically pieces of the integral, or for the centroid. Our results. 3 times HB. Okay, and now we actually have to use algebra to solve for this, to get our answer. So recall that I'm taking these two pieces here and multiplying them to get our answer. Oops, I almost forgot. This got turned around because we're multiplying by the reciprocal, since it's a division. So I'm gonna write that because it's kind of hard to see a function turned around or a fraction that's upside down. Wait, what the heck? Now I could see. Alright. Yes. Okay, multiplying all this together, then we're going to have these h's cancel out. We're going to have 1b cancel out. And our final answer for the centroid of the x will be 3b over 4. Oh, sorry, over 8, because a multiplies 2 times 4 here. This will be our answer for the centroid of the x. So x centroid will equal to 3b times 8 here. And here we have solved our example problem for the centroid in the x. Well, class, this has been my lecture presentation video, and I hope you enjoyed it, or it wasn't boring. Anyway, if it was, here's a picture of a shark. That's going to be my entire presentation. You